Our next speaker is Chris Zacny. Dr. Zacny is the Vice President of Exploration Systems at Honeybee Robotics, and he's presenting Planetary Volatile Extractor, PVEx, for prospecting in situ resource utilization.
Thanks very much. And I want to apologize. I had emergency, had to step out, but I'm back. Previous speaker, very exciting presentation, and I'm gonna be following on a very similar topic of extracting volatiles from a regolith. Next slide, please. One thing, so we started working on this over a decade ago, and we looked at a lot of different ideas how to heat up regolith and how to actually capture volatiles that are extracted from a regolith. What we found very early in this process is that it's not really about heating. There are many processes to actually heat up regolith and then volatilize, sublime away icy soil. The biggest issue is how do you capture these water molecules? We tried things like sniffer, where we put a heated perforated auger and heated it up, and nothing came out. Nothing. We didn't capture anything. Then we tried things like porcupine, a hot plate with the spikes and the internal perforated holes that we are hoping water molecules will sort of fly through to the cold trap. We got nothing. And we tried auger with external sleeve, and that actually gave us some water capture. But the best one was PVEx, Planetary Volatile Extractor, where we drilled a coring system into the regolith, heated up the core, and captured the regolith. So the lesson that we learned is it's not really about heating of regolith. It's about how do you contain the molecules and make them flow into the cold trap as opposed to into the space of vacuum. And this step is, capturing of molecules is 10 times more difficult than actually heating of regolith. Next slide, please. This is a close-up of operation of a PVEx. It's essentially a hammer drill with a coring auger, sort of like a similar coring auger that Apollo 15 used, a few decades ago. On the inside of the coring auger, we have a heater. So we drill down, we form this, we capture a core. Once we at depth, we heat up the icy auger. Ice sublimes away, creates pressure, and once it creates pressure, the further volatilization actually is easy because we're no longer doing heat transfer through radiation or conduction, but more through convection, which is significantly more efficient. And then water molecules under pressure, they flow up into the swivel and out from the swivel into the, say, for example, a cold trap. On the right-hand side, what you see is PVEx sitting inside our PVAC that we used to we drilled into NULHT2M, which is a Highland simulant with 5% water. We heated up and we captured volatiles in this balloon insert into the picture. Next slide, please. The PVEx, what we found is PVEx actually can be scalable. It could be sort of a system that you use to explore the subsurface. It's a great method of actually capturing information for science exploration. That's this, 3B right on top for like a follow-on to Viper. It could be Viper 2.0. It could also be used for production. We can scale up the size of a PVEx system, put more of them, and have redundancy through numbers, and use it for extracting significant amount of water. And finally, this is a great way for EPO. In one of our designs, we actually have a balloon, minor balloon that can be inflated by volatiles captured on the moon. And this is a great way to increase awareness and convince our younger our kids to turn into STEM. Next slide. The video that you see on the right-hand side is a test in NU LHT2M with 5% of water at minus 20 degrees centigrade. We actually have done a lot of drilling into these sort of formations with absolutely no problem. You can see we go through this with our hammer drill like through butter, so it's no problem in terms of drilling. Next slide. And then we start heating it up. Note that in this particular condition, we had dry regolith right on top, followed by 5-8% regolith below that. And maybe play this again if you can. And what you see is while we start heating up, this Mylar balloon starts inflating. This means that we actually have been extracting volatiles, and volatiles under pressure were flowing into the balloon. Next slide, please. And these are our tests. What you see on the right-hand side is this picture of the PVEx. In the middle, you see the picture of the extracted water. Picture of our cold finger or cold trap is bottom left-hand side. You can see actual ice that has been extracted. So this is an end-to-end demonstration under vacuum conditions, drilling, heating, and water extraction. On average, penetration rate was around 1 to 2 millimeters per second. We use on average, less than 100 watts of electrical power to just do the drilling. In most cases, we extracted 50% of water that was contained in the soil. This is actually quite important because the system that we have is relatively sealed, and yet we lost significant amount of water. So, and that's a sealed system. If you have an open system, you're going to be losing 99% of water. From a heating standpoint, a lot of heat went out through the walls of our metal auger, but there are solutions for this. Our auger could actually be made of fiberglass. Sort of, Apollo augers were actually fiberglass, boron fiberglass augers. And we can do the same thing to reduce, heat losses. Next slide, please. And from a production standpoint, we looked at how this could scale up for larger architectures. So if you imagine 20 centimeter diameter PVEx and 1 meter long, if you conservatively assume that 75% of all volatiles is lost, we assume we captured 50%. Here we say we capture only 25%. We assume that 50% duty cycle. So half of the time we're not mining and half of the time we're mining. We also assume conservatively that we only have 2% of water in a regolith as opposed to 3, 4, 5. So within a single year, one PVEx can capture 1 ton of water. 6 PVEx, like pictured in the middle in our mining system, can capture 6 tons of water. And obviously, you're not going to be sending one of these things. You really need redundancy. 10 of these mining systems can capture 60 tons of water per year. And that's water inside the tank. So the main advantage of PVEx system is it's scalable. It can address science missions goals and can also address exploration mission goals. It's a built-in redundancy. We essentially building more of the same. So if one of these things breaks, we can use another one. And it can be extremely adaptable, works with hard and soft material. And most of the ice is going to be below the surface. So you need something that goes 10, 20 centimeters below the surface. Next slide, please.
2 minutes.
2 minutes, great. And just one thing, that PVEx is essentially 90% Trident. Trident is a rotor-percussive drill that will be flying to the moon in November of next year as part of the Prime 1 mission on board of Intuitive Machines lander, and then again in November of 2023 as part of Viper rover. The difference between PVEx and Trident is the auger. Trident uses full-face drill bit, so it essentially drills entire borehole. PVEx captures a core. It's a coring drill, but everything else is exactly the same on Trident and PVEx. So to fly to the moon on Viper 2.0, Prime 1 2.0, the only thing we would do is change from a Trident auger to the PVEx auger, and while preserving this very important flight heritage. Next slide, please. And I'd like to acknowledge the SBIR program and Jerry, Julian, and Jackie Quinn from NASA Kennedy, Glenn, and NASA Johnson. Thank you.
Okay, thank you.